Hello everyone and welcome back. In this video we will be looking at doing questions 5 and 6 for the option 2 case study in the 2019 past paper for hardware systems applications. Now in this question, for this design option, it requires us to design a VGA controller, and it gives us some diagrams explaining the operation of the VGA controller. Now, before we even approach this question, we need to ensure that we understand exactly what a VGA controller does. All right, so before we even think about the finite state machine or the block diagram, or before we think about the code, we need to look at exactly how a VGA controller works. So before we do that, let's switch to Jamboard here, and I want to bring to your attention this scenario here. So just imagine in those older cathode ray style televisions, right? What we refer to as those big back TVs, right? What happens is, let me see if I can draw this a little better. VGA controllers typically work with cathode ray tube televisions, all right? We know that these VGA screens and these older monitors are typically of a resolution of 640 by 480 pixels. All right? How these work is there's actually an electron gun somewhere behind the back of this television here, which fires electrons with red, green, and blue colors on the screen. Every time the electron gun fires an electron, it does so on a particular pixel coordinate. And the order in which these electrons are fired to the screen in order to create an image is horizontally at first, pixel by pixel, like this, until we have one entire line of display. And then the electron gun, snaps back to this first position, and some control system tells it to snap back to this end of the screen in the horizontal direction, and it also tells it to fire down to the next line, and then it creates another line of pixels, then it snaps back and it creates another line of pixels, snaps back and it creates another line of pixels, until we have 480 lines of pixels in this direction, giving us one entire image. All right, so we have 480 lines in total, assuming the resolution is 640 by 480, and we have 640 pixels in this direction for each line. And the electron gun fires these electrons at such a fast rate, it's usually at 60 Hertz refresh rate per line, that it generates one line of the image in 1/60th of a second. That's 60 Hertz. And the human eye actually doesn't see the time in which it fires those electrons to the screen, so we just see the picture on the TV as one image. All right, so let's look at this diagram here. This diagram is telling us something about horizontal syncing and video lines, right? And it's telling us something about vertical syncing with the video frame. Now we have these blue outlines here magnifying what's going on in one of these video frames. So in each of these vertical lines, or in each of these vertical video frame columns here, we generate an entire horizontal row of video per line. So what exactly happens is the horizontal sync, that's this line here, this signal here, controls how the electron gun is firing these electrons across the screen. So when this sync signal starts here, it basically tells the electron gun to snap back to this leftmost point here and generate this video line. That's this horizontal video line, a single line across the screen. Okay? After that occurs, within this little window here, the vertical sync pulse tells the electron gun to start firing lines one spot down or one line down. So we start now, the photon gun now is going to fire electrons on the second line, and the end of this horizontal pulse here tells the electron gun to snap back to this point. So those two signals, the vertical sync and the horizontal sync, tells the electron gun to go to the next line, snap back to the leftmost position, and generate another line of images there. And once those 480 lines are generated, in 1/60th of a second, we see the image being drawn on the TV, or we see the image on the screen. All right, so let's look at these signals in detail here, paying particular attention to the horizontal signals on the right. So what happens is during this, so initially, before we start our sync pulse, we are in some sort of waiting phase here. In other words, we are waiting for the electron gun to snap back to that initial position. For it to snap back, the sync pulse goes low, and that sync state, or that sync pulse, exists in this state for that particular amount of time. All right? Then, after it's synchronized, like this, we wait a little bit, this amount of time here, then we generate that video line horizontally. After we generate the line, we wait some period of time again, and then we fire the sync pulse again to tell it to snap back to the left edge of the screen. All right? So this entire process of one synchronization pulse to the other takes place in this window of time labeled A. The area before a sync pulse, be it on this part here or this part here, is typically referred to as the front porch. Likewise, the area behind the sync pulse, be it the point between the sync pulse and the start of transmission of the video, or the point after the sync pulse when it snaps back the electron gun, that is referred to as the back porch. Okay, so let's look at exactly what we are required to design here. To interface with a VGA screen, you need to create a VGA interface. The timing is shown in figure B2, so we saw the timing here. All right. Your design needs to create a finite state machine to send out one horizontal line, so we don't have to worry about generating the entire image on the screen, which is actually good for us. We only need to look at generating one horizontal line. In other words, just the first line here. All right, and assume you have a clock with the correct frequency. So what this means is that we no longer have to worry about calculating frequency divider count values. Okay, and assume that the timings shown on the diagram correspond to the following number of clock cycles. So what that means, first of all, is because we are only looking at creating a finite state machine to send out one horizontal line, we're not really concerned with the vertical sync stuff. So we could actually ignore the vertical video frame and the vertical sync. Likewise, we could ignore the timing diagrams for the vertical pulses. We are, however, because we're sending out one horizontal line, concerned with this diagram, and we're concerned with the times A, B, C, D, and E in sending out a horizontal line together with its synchronization pulses and the video lines. Okay, so the times here, it tells us that the entire time for me to, so let me just clear up this diagram a little bit. Right, it's telling me that the time period A, which is the time period between synchronization pulses, that's the total time taken for transmission. How do we know that? Because we sync to start transmission. After we sync, we wait this amount of time. Okay, so let's just, so the total time of transmission is between the falling edges of the sync pulses. So you'd notice that the time A ranges from falling edge to falling edge, and that's when we start synchronizing to tell the electron gun which parts of the screen to snap back at. Okay? When we are synchronizing, we wait in that we are in that synchronization state for B clock cycles. B corresponds to 100 clock cycles. The back porch of this signal, C, is a little bit of a waiting period before we actually start transmission. So that back porch area there corresponds to the time C, which is 55 clock cycles. The time here, D, is the time for the actual video transmission. And it says here that that time is 640 clock cycles. Now, we know that VGA screens are typically 640 by 480 resolution, so we could assume that that means 1 clock cycle per pixel on that line being drawn. Not that that's important, but it's just nice to know. After video transmission, we have another waiting area, which is now the front porch of this second sync pulse. Sorry, the front porch, because it's before the sync pulse. So we have this front porch waiting state here, which is time period E, and that takes place for 20 clock cycles. So if we add up these numbers, 640 plus 100 plus 55 plus 20, we get a total of 815 for the entire time taken for sending out one horizontal line to our VGA screen, which is exactly what we want here. Now back to how the VGA controller works. We typically require 5 signals for a VGA controller. The electron gun, which fires out the RGB values for the pixel colors to be generated in the image, require an R output, a G output, and a B output. And then, of course, we know that we need those horizontal sync and vertical sync signals to give us the snapping back of the electron gun left to right and telling the electron gun to fire the electrons in subsequent lines. So we need our V-sync pulse and our H-sync pulse. Of course, for our purposes, we are only really concerned with H-sync here because we are only looking at sending one horizontal line out. Okay? So in these timing diagrams here, the horizontal sync and the vertical sync signals correspond to those V-sync and H-sync outputs of our VGA controller, and our RGB output corresponds to the video line and the video frame in each of these here, right? Which is why we only need R, G, and B. Now there's a nice little guide that explains VGA controllers very much similar to the format of the exam. So I will also include this link in the description of this video. Okay, all right, so onto another page. Let's see what we are required to do here. Okay, so as always, with question 5, we are required to draw the block diagram of the system and state any assumptions that we're making. And part B requires us to draw the state transition diagram. So let's look at option 2, question 5, part A. Okay, so the block diagram for our signal, our inputs are going to be a clock signal. The reason we need a clock is we know it's a sequential circuit, so we need a clock. We need our reset. We need some RGB input. This format will stick for any of the following, any of the other VGA controller past papers that we will look at. Our output signals, that is the signals that our VGA controller is required to provide, are these 5 signals here. Okay, that's our H sync, our V sync, our R, G, and B outputs. All right. Note that there's a single RGB input with multiple single RGB outputs for R, G, and B separately. Okay. All right, some of the assumptions. All right, we know we always need to put assumptions to get the full 5 marks there. All right, so we have assume an active high asynchronous reset, kind of like with the previous question. We're going to state that this allows us to start in a known state. That's going to be our initial state. All right. A second assumption. There is a requirement for the pixel color information as input. All right, that pixel color information refers to our RGB input. So there is a requirement for pixel color information, and this is what dictates what R, G, and B are going to output. As input, right, and yeah, that's basically it. Another assumption is even though this design is for one horizontal line, right? Because remember the question said for us to design for sending out one horizontal line, not the entire frame of video. All right, so even though we're required to design for one horizontal line, we include the vsync signal for completeness. All right, and it's just because every VGA controller relies on those two signals. All right, great. So that basically takes care of part A of this question. So now we're going to go on to the state transition diagram. And that state transition diagram, of course, we are going to extract the states from this timing diagram here. So we're going to have a state where we are initially waiting for the sync pulse to start up, and that's going to be our initial state. We are going to have a state for synchronization here. All right, then after we synchronize, we are going to have a state, a small wait state, which is that back porch waiting state here. Then we are going to have the video transmission state. After transmitting the video, before we synchronize the electron gun again, we are going to have another wait state that corresponds to the front porch waiting state. And then finally, we are going to go back into another sync state where, depending on how the vertical frame goes, we are going to transmit another line of video, etc., etc. But we are only designing for one line of video. Okay? So these states, we could go on to this new page here. It's question 5, part B. Let's just list the states here. We're going to have our wait state. I'm just putting initial so we know where the reset signal takes us. We are going to have our sync state. Right? Which corresponds to this period here. So I could actually put B clock cycles in here. I'm just going to put B clock cycles. Right, then we are going to have the back porch, yes, the back porch wait state. Which we know occurs for C clock cycles. Then we're going to have our video transmission state. Which is for D clock cycles, that's 640 clock cycles. Then before we synchronize again, we have that front porch waiting state. Right, and that waiting state there, corresponding to this, is E clock cycles. All right, great. So we can go on to write the FSM, draw the FSM for this. All right, so we said that we had this, what we called it the wait state. wait underscore state. Right, let's draw our state bubble around there. And this is our initial state, of course, denoted with this dot and arrow coming from nowhere. Right? And our reset signal is what causes us to go into that state. All right? Then we're going to have a start signal, which allows us to move from that wait state into the synchronization state. And that start signal corresponds to this falling edge here. All right? So we're just going to call it start. And that takes us into the synchronization state here. Okay. Great. We wait in this synchronization state for B clock cycles, which is 100 clock cycles. Of course, to keep track of these cycles, we are going to use another counter. It's just we assume that the clock has the correct frequency, so we don't need to calculate these count values. We're actually going to use these numbers here as our count values for the number of clock cycles. Okay, so what that means is the input to the system for me to transition out of this sync state is going to be 100 clock cycles having elapsed. Right? Now for me to keep track of these clock cycles, I'm going to need a counter, because until the number of clock cycles is equal to 100, I'm going to have to increment this counter, much like I did in the previous question. Counter is equal to counter plus 1. Then, out of that sync state, I am going to go into this first back porch waiting state here. Right? So I'm going to call that my back porch. And back porch is just the terminology for VGA controllers, right? Back porch wait state. Okay, and of course, I'm going to stay in this wait state here for C clock cycles, which corresponds to 55. All right, in other words, the value for me to come out of this is after 55 cycles. So my counter here has to increment again, and I'll say after 55 extra cycles. And the reason I'm putting extra here is because, remember, we're using the same counter and 100 cycles have passed here. So in other words, I'm going to look for 155 cycles, or the value of my counter being 155, right? So after 55, extra cycles, I am going to go into my video transmission state. Right? And of course, in this state, I have to count the number of clock cycles that have passed. And it's only after 640 extra cycles have passed, in addition to the 155 from before, then I'm going to transition out of this state. So the input to the system for this arc to allow me to transition from this state into the front porch waiting state is going to be after 640 extra cycles. All right. Then I'm going to go into my front porch waiting state here. Right? and now corresponds to this part of the diagram, part E, for E clock cycles, which is 20 clock cycles. I am going to stay here. Right, so I have to increment my counter. And after those 20 clock cycles, that's when I start the synchronization for the next line of video. Okay, so I'm going to transition back into the sync state for the next line of video after 20 extra clock cycles. Right? That's basically it for this finite state machine diagram. It's pretty simple, simpler than the traffic light one. So let's determine some things. Our counter value in our sync state is going to start counting at 0. When I get to the back porch state here, I need to keep incrementing the counter until another 55 has passed. So I'm going to check when the value of counter is equal to 155 in this case. And that is when I'm going to transition to my video transmission state. And after 155 cycles have elapsed, I have to determine after another 640 have passed. So I will be looking when the value of count is equal to 155 plus 640 is equal to 695. And then after that, I'm going to wait another 20 clock cycles corresponding to the window E here, right? Because E is 20, and that gives me 795 plus 15. I'm going to check when the counter is equal to 815 for me to transition back to the sync state. And of course, 815, that number, corresponds to the time window A, which is the total time of transmission of that single video line. All right. So yeah, that's it there for 15 marks. Yeah, which pretty much takes care of that part of the question, right? Okay, so let me just remove, actually no, let me leave these values here so we'll have it for typing the code. Okay, so on to question 6 now, which is going to require us to write code for the finite state machine, the VGA controller. So we're going to implement this finite state machine for the VGA controller. All right, so let me open Quartus again. And things are pretty similar to before in terms of how we're going to create the project, etc. So I'd like to, let me open this project. And the reason I'm opening this is because it's in this folder called Past Paper 2019, okay? So I'm going to add a new file to this project. Right, you of course could create another project if you wish, it doesn't matter. It's just for the purposes of this video, I'll be using the same project that we were using for the traffic light question. Okay, so the code of course is going to start off with my package declaration. I could get these things out of the way. I'm going to have my standard logic library for my bits, and I'm going to have my numeric library for my integers and my integer math. Okay, great. So the entity now, I'm going to call this entity VGA Controller. And it, of course, is going to correspond to our answer from question 5, part A, which is this here. So we have these inputs, clock, reset, RGB input, and we have outputs H-sync, V-sync, R output, G output, and B output. Okay, so yeah, let us get started with that. So we have our clock and our reset, which are inputs of type standard underscore logic. We have our RGB input, which we could bundle as a 3-long vector. Okay, so we have our R inputs, our G inputs, and our B inputs. These are inputs. And we'll just treat them as 4-bit values for now. We have our single HSync bits and VSync bits. Right, and of course we're going to have 4-bit outputs for R, G, and B. Okay, so we're going to have R output, G output, B output. Those are outputs, type standard logic vector, and of course they must be the same width as their input counterparts. Right, so that basically takes care of the entity there for nice 4 marks question. So now we're going to go on to the architecture of this VGA controller, which of course we know the general processes that we have are 2 processes for the finite state machine, and a process for the counter and a process for the output. Okay, so let's go on to the architecture now. So I'm going to say architecture behavioral of VGA controller is, and of course before we begin the body of our architecture, we're going to need to define type for the state machine, and of course just as before we need comments for the code to kind of say exactly what we're doing. Okay, so I'll say define the states for the state machine. Okay, so I'm going to use my keyword type here, and I'm going to call this one VGA state, and my states are, I'm going to have our wait state, our sync state, backport wait, video transmission state, and front port wait. Okay, so this is my initial wait state. I have my synchronization state, I have my backport wait state, I have my video transmission state, I have my front port wait state, and of course that takes us back to the sync state, right? So that's it for the states for this finite state machine. The next thing I'd like to do is to define signals to hold the current and next states. Okay, so I'm going to have signals for current state and next state. These are going to be of data type VGA state. That's that data type that we just defined above. We're going to initialize them to wait state. Just for the sake of giving it some initial value, we're going to use the initial state. All right. The next thing I need to do is to define a signal for the counter to monitor the number of clock cycles that have elapsed. And I'm going to call this VGA count. It's an integer that's going to range between 0 and 815. Okay? All right. So now we can actually start writing code for the body of the architecture. Now the 4 processes that we need are the FSM, the FSM processes, which could be broken down into our next state logic process and our state transition process, right? This one determines the state transition logic, whereas this one takes care of actually assigning the current state to the value of next state, right? Then we are going to need a counter process, and finally an output process. So we typically have 4 processes for these questions, all right? So let's first take care of process to determine next state logic, okay? So I'm going to call this state transition logic, and of course you could give this any name that you want, huh? All right. Before I write the sensitivity list, let me just write my begin and end keywords here. Cool. So this process is usually always sensitive to your current state. All right. And in this case, it's going to be sensitive to changes in the count value, VGA count. Of course, that corresponds to the number of clock cycles that would have passed, right? And we're also going to have it sensitive to the reset signal. Just in case we hit the reset button, we want to calculate the next state logic as the wait state. Okay, so the first thing, and this is just a rule of thumb for all state transition logic processes, the first thing that we want to do is assign next state to current state. And of course, remember that that takes care of if none of those case when statements are satisfied, we need to stay in the current state so that when next state is assigned to current state in the other process, it's as though current state is being assigned itself and we stay in the process. And that takes care of the case where we have the arrows transitioning back to the states. Okay, so this is just a nice little rule of thumb. We always need this line of code in that state machine logic there. Okay, so first thing I want to do is my case statement, and I'm going to check the value of the current state. Right, let me just end this off here one time. All right, so in the case when my current state is equal to wait state, in other words, when I'm in the wait state, what happens? Well, if some signal start is equal to 1, then our next state is going to be our sync state. All right. This corresponds to this start bit here. Now, we said that the start signal is defined by this sync pulse going low, right? But let's look again at what are the inputs to this device here. We just have a clock, a reset, and that RGB input. So what we may want to do now is to add a start signal here, right? And yeah, we'll just have that as an input into this design. So what I will do is I will modify the entity here to include a start signal. And of course, that will be a single bit value of type standard underscore logic. Okay, so if start is equal to 1, then next state is equal to sync state. And that just starts off the finite state machine loop that we will be stuck in afterwards. Okay, all right, so when the current state is now in the sync state, well, what happens? I want to see if 100 clock cycles have passed, right? So I would like to see if VGA count is equal to 100, then the next state is going to be, which is it? The back porch wait state. Okay. Then, when the current state is equal to back porch wait state, if the VGA count is, if 55 extra cycles have passed, depending on the value of counter, then I want to transition. Now again, I can't check to see if count is equal to 55 because I have to take into account the fact that counter is equal to 100 when I'm in this state initially. So to track that 55 extra cycles have passed, I want to look for the value of 155. So if my VGA count is equal to 155, then the next state is going to be the video transmission state. All right. Now, when the current state is equal to the video transmission state, this is the state where I will be sending my output. Of course, we don't take care of output in this process. That is going to happen in another concurrent process. We are only taking care of what is going to be the next state based on my current state. So when I'm in the video transmission state, if my VGA count is equal to, and I have to determine if 640 additional cycles have passed. So if my count is equal to 795, that is when we want to transition to the front porch wait state. Right? And then finally, when I am in the front porch wait state, this is our last state, we know that after 20 cycles have passed, in other words, 795 plus 20 giving me 815 for the value of count, I'm going to transition back to this sync state here, of course, for the next line of video transmission. Of course, we're not taking care of the next line of video transmission, but we still need to set it up. We need to set it up, all right? So if my VGA count is equal to 815, then my next state is going to take me back to my sync state. All right, and of course, the last thing we need to do for any case when statement is that default case, and that is always necessary for a case when statement. The code would not compile if you don't have this default statement. Okay, so when others, our next state is going to default to our initial state, which is our wait state. Okay, and that takes care of this first process, which handles determining next state logic. Okay, let me just put my end architecture statement here so that I could, I'm going to call this VGA Controller. I'm saving the file here in the same folder, and I'm going to, well, because I'm using the same project, what I'd have to do is set this as a top level entity. Of course, if you created a new project, you don't need to do that. But just for me to compile it, I have to do that, okay? And the reason why you always want to compile it is to ensure that you don't have errors along the way, so that you're not bombarded with errors when you finish. Kind of like I have here, right? So let's see what is this problem that I have here. Near text 815 expecting and, or plus, or minus, or 2, or 2. All right, then I have some problems there. I'm not sure. Let's recompile and see. Entity VGA controller is undefined. VGA underscore controller. Right, so I created the top level design entity here as VGA underscore controller, but the name of it was VGA controller without the underscore, so it was throwing an error. Okay, and minor errors like that, while your code would not compile, it does not affect the answer. You can still get full marks for a question like that if you make a minor mistake like that. Okay, so don't worry about that too much. All right, So now we could go on to the next process, which is the second process related to the finite state machine, which takes care of the actual state transition logic. Okay, so we are going to have I'm going to call this process VGA state proc. It's going to be a process which is, of course, sensitive to my clock and reset. Now, when you're looking at the solutions, you'll see that they use wait statements to generate the clock. And because they have wait statements, they would not have a sensitivity list like this. Remember, a process with a sensitivity list always it cannot include wait statements, and vice versa. A process with wait statements cannot have a sensitivity list. All right, so this is our process to store the current state based on next state logic determined above. Okay, so I'm going to have my begin and end keywords here. All right, now we stated in our assumptions that we are going to have an active high asynchronous reset. So because it is an asynchronous reset, it is not governed by the clock, so it takes priority over the clock. So the first thing we need to do is look at if our reset is high. The reason why we're looking at if it's high is because we said it's active high, right? So if reset is equal to high, then we know that our current state is going to be equal to the initial state, which is called wait state. And then I'm going to look at how the state is going to transition on every rising clock edge. All right, so on every rising clock edge, all I want to say is that my current state is equal to next state, and that's whatever was determined for the value of next state in this process above here. Okay, and that is it for the second process corresponding to the finite state machine. Okay, those two processes by themselves, out of this, how much is it? 15 marks, that's worth about 8 marks. All right, so once we know this stuff here, once we have determined the finite state logic, we get half the marks. Okay, the next thing that we'd want to do is our third process here, which from our list above says that we are going to write our counter process. Okay, so let's see what the sensitivity list of this process is going to be. It is going to be sensitive to changes in my clock, because on every rising edge I would want to count up, right? Okay, so I want to say if clock event and clock equal 1, because we know that each of these count values corresponds to one of the clock cycles, because it says we're assuming that the clock is the current frequency and that we only need to track these number of clock cycles here. All right, okay, so on every rising edge of the clock, what we would want to do is check to see what is the current state that I'm in. So let me put the end if block here for that if statement. Let me have this nested if statement here now to check what is the current state. So if I'm in the wait state, notice that that is the only state that I am not counting in. In all of these states, I want to count except for the wait state. So at this point in time, that's the only time my count value is going to be equal to 0. And that is where I'm going to initialize that count value there. So VGA count is equal to 0. Of course, no quotes around this 0 because we're dealing with integer numbers here. All right. the clock value here will have single quotes because that is a standard logic value. Okay, else if, and now I'm going to take care of my states here. So I'm going to put this end if statement here. And this part of the code is where I'm going to list all the states that I want to count in. So if my current state is equal to the sync state, or if current state is equal to the back porch wait state, or if current state is equal to the video transmission state, or if current state is equal to the front porch wait state, then that is when I would like to increment my count. So VGA count is equal to or assigned the value of VGA count plus 1. Right? That's basically it. The fact that we limited the range from 0 to 815 here means that when we hit 815, we automatically roll over back down to 0. Okay? And that basically takes care of the counter process. So the last process that we would need to write now is the output process, which determines how the RGB input goes to the RGB output lines. Okay, so this is now, sorry, let me just finish this comment here. Process to count number of clock cycles. And finally, we have a process to, sorry, we'll just call this one the output process. Right? And of course, this is always only dependent on whatever the value of the current state is. So as soon as the current state changes, that is when our output is going to change depending on the state that I am in, because that's how finite state machines work. All right? So if I am in the sync state, remember, the first thing I want to do in this sync state is to send this pulse low. So that sync pulse corresponds to my H-sync output here. So the first thing I want to do is if I'm in the sync state, then my H-sync value is going to be equal to 0, because you have to pull it low for it to start. Else, it's going to be high, right? And of course, we know that that synchronization signal allows the electron gun to snap back from the right end of the screen back to the left. Okay. So, right, we'll have two output processes. So we'll have one for the H-sync, and we'll have one for the actual RGB output. So this is now my RGB output proc. And again, this is dependent on your current state. Okay, and this just takes care of the reason why we split this into two processes is one handles control signals for how we output the image, and one handles the actual pixel information. All right. Okay, so if I am in the video transmission state now, that is the only time I'd want to send out output on those lines. Right? And then if I'm in that state, then our output is just going to transition whatever our input is, that 4-bit value. My green to green, my blue to blue, right? Else I will just output black values or zeros. These are 4-bit values, remember, so we're just gonna send 4 zeros out there. Alright, so I'm going to end out this process here called RGB output proc, and that takes care of the processes for this design. Let's compile our design. Here, we could actually bundle these two output processes into one if we want. It's not a problem to do so. Right? So yeah, that takes care of the code for the VGA controller. Once we know these 4 main processes to include in any of these questions, that's basically that 20 to 25 marks there. Okay, so that brings us to the end of this question. That takes care of question 6 parts A and B. And of course, as always, for us to submit this for evaluation, we need to go into our Altera folder, wherever that code is stored, look for the name of our project folder, and select the appropriate code file, add it to a zipped folder, and upload it to either the flash drive or Moodle. All right, so that's it for the 2019 paper. The next set of videos that we'll look will handle the 2018 paper. So thank you for tuning in, and that's it.